Hello students, welcome back to Galantis Academy. I'm very happy to have you back. So in today's video, we'll be discussing simple harmonic motion. I'm pretty sure you have a basic idea of what simple harmonic motion is, but if you don't have to worry, as during the course of this video we will have we will explain simple harmonic motion in details. Also, in this video we are not solving any question, though all the formulas you need to tackle any question in simple harmonic motion will be explained and given in this video. In case you want to just learn how to solve questions only, check out our playlist here on YouTube. Alright, so what will we be discussing in today's video? We have a brief introduction of what simple harmonic motion is, explain what harmonic is, that's what this is, and also what motion is, condition that has to be met before a motion is considered simple harmonic motion, terms related to simple harmonic motion, phase in simple harmonic motion, then most importantly simple harmonic equations. Then we are going to conclude and have an overview of what we've learned. Now let's dive in. Alright, so simple harmonic motion is the idealized vibratory motion, a system that obeys Hooke's law undergoes. Alright, so key takeaway here is a vibratory motion. So we know that simple harmonic motion is vibratory. Do you understand? And a system that performs it is closely related to what? To Hooke's law. Is that right? Good. So we can also say it is an oscillatory motion with acceleration proportional to displacement and directed towards a fixed point. Alright, let me make this visual. Okay, let's assume we have something like this, a particular system. This looks like a pendulum. Alright, so let's assume something like this, and it will come in this direction, this will come in this direction, it can also go in the opposite direction. That's from here it can go to this place, from here it can go to this place. Is that right? So what this particular statement is trying to say is that in simple harmonic motion, acceleration is proportional to displacement. And here in simple harmonic motion, we represent displacement as x. Is that very, very clear? And it's always directed towards a fixed point. This place is the fixed point or equilibrium, or what? Place of what? Equilibrium. Now, there are certain signs that are associated with acceleration being directly proportional to x, and on and on and on and on like that. But I don't want to move fast. I want to go at your pace. I want to ensure that you understand all what I'm saying. Is that very, very clear? So I'll go bit by bit, step by step until we are properly built. Okay, first, before you learn anything, regardless the subject matter, regardless the discipline, right, you have to first understand what that topic is. For instance, if I come into your class and I say, oh, today's topic is grammar, right, or one huge name like this, right? First of all, understand, okay, what does grammar really mean? Okay, what does this really mean? Okay, forget about simple combination, forget about the topic now. Let's break it down, right, down to its roots. Now, what does harmonic mean and what does motion mean? Alright, you've seen the answer, but then no worry, pause your video and tell me what it means in the comment section. Can we do that? Good. Now, harmonic is something that we have heard countless times. right? Both in sound wave, you've heard of harmonic, and other subject matter too. Motion, definitely. You've been taught motion right from your younger days, right? When you're in secondary school, right? That's in GSS classes. You've known what motion is, so this won't be hard for you to comprehend. Okay, so harmonic refers to the regular repeating nature of the motion that can be described by sinusoidal function. Okay, let me come again. We have to know that harmonic motion, right? In harmonic motion, there is actually a regularity. Let's put it here. There is a regularity. So if it means that if it's moving like this, then it's continue moving in that direction. Not that it will move like this, then go like this, then come here, then go here, then come back. No, it's what regular. Is that correct? So what we know about simple harmonic motion is that its kind of motion is regular. Its kind of motion is regular, and because it's regular, it can be problems under it can be associated can be solved with what? Sinusoidal function. Now sinusoidal function is just like a repeating motion itself. I get it. Any motion that repeats itself, right, is called sinusoidal. Is that clear? And we can see sinusoidal in when we are discussing about wave and the likes like that. Is that clear? Now, what does motion really mean? What does motion mean? So motion is simply the act of something changing its position over time. So now if I have a ball here, and after a period of time I find the ball at this position, what has changed? The distance has been altered, and the position has also been altered with respect to time. I got it. So in this kind of scenario, we say that motion has been accomplished, right? The motion has been registered. Okay, so key takeaway. Note that not all simple harmonic motion are oscillatory. Sorry to say that. Note that all simple harmonic motion are oscillatory, right? And also periodic. Periodic, it's kind of mean is regular. I get it. When they say periodic, it's kind of mean what? Regular. So whenever you hear, you just woke up from sleep and they ask you, okay, now what does simple harmonic motion mean? Don't worry yourself. The first thing you have to say at least is what? Is an oscillatory motion. I get it. It's an oscillatory motion. But what of oscillatory motion? Are all oscillatory motion simple harmonic motion? Definitely not. Oscillatory motion is just like it encapsulates most repetitive motion. I guess it encapsulates. But I will tell you very soon why not all oscillatory motion are simple harmonic. We are coming to that. Don't worry. Alright. So oscillatory motion is also called harmonic motion of all the oscillatory motions, wherein the most important one is simple harmonic motion. I get it. So simple harmonic motion is frequently called sinusoidal motion because of its resemblance to its graph which is sine or cosine curve. I get it. So I'm coming to this version now. This is where I'm actually going to. The main feature of simple harmonic motion is that the system oscillates at a single frequency. It oscillates at a single frequency, and this is exactly what makes it simple. Hence the name simple harmonic motion. Is that very clear? Now, in the previous slide, I said that not all oscillatory motion are actually simple harmonic motion. Is that clear? Good. But why is that so? Why is that so? It's just the reason why we say not all oscillatory motion is actually simple harmonic motion is because of simple harmonic motion can only exist at a specific frequency and continue at that frequency. It meaning that any frequency that alternates itself rapidly, though an oscillatory motion, cannot be described by simple harmonic motion. Is that very, very clear? Good. And we also call the simple harmonic motion sinusoidal motion. And when I was saying sinusoidal, right, I referred it, or I linked it with waves. Is that very clear? That is repetitive. Is that very clear? Now, in wave, we see that the cosine curve and the likes like that. Is that very, very clear? Alright, so what are the conditions we have to meet before we say, okay, a motion or an oscillatory motion is simple harmonic motion? Right, one of them that's what we call at a particular frequency, the frequency has to be more or less constant, I guess, and so we have that as a thing already. So a body is set to undergo simple harmonic motion if it satisfies the following points. Now, there are only 2 points you have to remember for your exams and your Austin exams. Alright, so the first is that its acceleration is always directed towards the fixed point. Alright, so just like when I started, I drew something like this, and at a particular period of time, at a particular point in time, we can have something of this nature. Right? So it's always directed towards this point, always directed towards the midpoint, the fixed point. Right? Same as this. If it's at this point, it comes to this point. Do you get that? Unlike our natural car, right, which when we talk about acceleration is literally moving forward. I get it. It's literally moving forward under changing velocity. I get it. Now also, acceleration is directly proportional to the distance from the point. I said that acceleration is directly proportional to the distance or the displacement. And displacement, we can also say displacement is, right, we can also say displacement is also referred to as what? Distance. Is that very clear? Now, what are the terms you have to know for you to understand simple harmonic motion appropriately? The first is displacement. I've said displacement several times. Alright, so this refers to the distance of an object from its equilibrium position. Right? This refers to the distance of an object from its equilibrium position. Now, just like we have that, like this, right? This place is not what? The displacement. I get it. This is the equilibrium. This is what? The equilibrium position. Is that clear? At a given period of time. So this displacement actually measure how far the object has moved away from its center position. Alright, so next is amplitude. What do you understand by amplitude? So amplitude and displacement are interconnected. First off, why are they interconnected? Now, they both refer to distance. They both refer to what? Distance. But amplitude is more or less more specific, as it refers to the maximum displacement of an object from its equilibrium position. Is that clear? So if during if the whole at the end of the whole circle, right, this body attain this particular height, attain this particular position, from here up to this point is regarded as the amplitude. Is that very clear? Is regarded as the amplitude. So amplitude can be equal to displacement, but can never be less than the displacement, right? Okay. The next is period. This is simple. Everyone knows it. So period. When you talk about period, what do you mean? What are they trying to explain to the person you're referring to? Now, period is the time taken for the system to complete one cycle. It's as simple as that. It's actually the time taken for a system to complete one cycle. So also we can also say that is the number of seconds per cycle. number of seconds, right, or time taken per second. And now per second, we are talking about per second. We're literally talking about what? The number of oscillation. The number of what? Oscillation. So period, which is represented as t, which is denoted as t, is equal to what? Time over n. N referring to number of oscillation. Is that clear? So note this formula and remember it. Very, very important. Now, time period is also equal to 2 pi over angular frequency. Over what? Angular frequency. I'm going to explain very soon how we came about this formula, because I'm pretty sure you know all the formulas, right, of angular frequency. So you might be wondering, oh, how come? So don't worry, follow me as we proceed. So the next is the frequency. Now the frequency, this is the number of vibration. Now let's write, this is the number of vibration made per unit time, or the number of cycles per seconds. So frequency, which is denoted by f, is equal to n number of vibration over time. Simple as that. So it's just like the reciprocal of this. So what's your brain telling you? It means that if I say f equal to 1 over t, I'm still correct, since it's just like they are just like reciprocal. I guess, and they are literally like reciprocal. So frequency is just what? Inverse of period. Exactly. Now I didn't tell you what the SI unit of period is. So what is it? Can you comment in the comment section? Now the SI unit of period is seconds. Exactly. It's as simple as that. What of frequency? What is the SI unit of frequency? Now, no big deal. We can say per seconds, or we can say hertz. Right? We can say what? Hertz. That's in respect to the man who discovered it, who came about frequency. Right? Good. So from our basic understanding in physics, we know that we will remember this formula. We will always remember this formula. I guess that is angular frequency is equal to 2 pi times frequency, right? So if we make f being frequency the same way the formula, we have w over 2 pi. W over 2 pi. Now, how do I reach this? How do I get here? Now, we know that f is equal to 1 over t, meaning that t will also be equal to 1 over f, right? Good. So if I bring it here and say f equal to angular frequency over 2 pi, so f is equal to 1 over f being frequency is equal to 1 over period. So I'll say 1 over period being t is equal to w over 2 pi, right? So cross multiply, we have wt equal to 2 pi. Divide both sides by w, right? Divide by w, this. So at the end of the day, we arrive at t equal to 2 pi over w. Is that very clear? Which is similar to this. Is that very clear? Good. Alright, so now, common occurrence in simple harmonic motion is restoring force. Restoring force. You come across this several times, as long as we are treating anything under simple harmonic motion. Now, when they say restoring force, what does that mean? We understand what force is, right? Which is a pull on an object. Good. Now, restoring means it tends to It's restoring something. Let me put it simple. Let me not complicate things. Right? It's restoring something, like it's bringing about a particular process. I get it. So a process that wants to go on extension is being brought back. It's being brought back each time. So you got an idea what restoring force is now. So let's go. Let's dive in. So this causes the back and forth oscillation. So restoring force causes the back and forth oscillation. Clear? It is the force that constantly pulls the oscillating object back. It is the force that constantly pulls the oscillating object back towards its equilibrium position. Is that clear? The point where it is at rest. So equilibrium position is the point where it is at rest. But one thing, in short, two major characteristics of a restoring force that you must never ever forget is that it opposes the displacement of the system. Alright, look at this. Let me give you this as an example again. Look at this. Now, where do you think the force will go towards? This point, of course. This point, of course. Now, if it's going towards this point, what is happening? What happens to the displacement? It's literally reducing. The displacement was reducing. Alright, then I don't want to go into details now. I will explain that again. But what you have to note is that it opposes the displacement of the system. Clear? Good. And also, it is necessary. And what you have to note about restoring force again is that it's necessary if vibration is to occur. Right? So whenever you hear restoring force, therefore that's a vibrational system. Alright. So for a mass at the end of a spring, stretched spring pulls the mass back towards the equilibrium position, while a compressed spring pushes the mass back towards the equilibrium position. So I'm going to use two scenarios to explain to you the relationship between force and displacement. This is a simple pendulum, right? So if the force is directly proportional to x, we all know that. But now, is it just literally x? No, it's not just x. Why? Because as the force increases, right, the displacement actually reduces. So force is directly proportional to negative what? X. Is that very, very clear? Is directly proportional to what? Negative x. Okay, now in some cases we can actually use a spring mass system. So we have something like this. Like this is a compressed string, and we have another which is more loose. We have another that's more loose. Okay, so in this particular one, this one is recoiling, right? That's moving in this direction, right? At some point it will come down. You get that it go down, while this is more like might be at the bottom now and it's going up, right? This just reached the top, it might be at the top now, so it's literally what trying to go down. Is that clear? Alright, so force is directly proportional to x. So what of phase? When I say phase, what does phase really mean? Phase refers to a specific point in the circle of the oscillation. It indicates the state of the oscillatory system. Is that clear? It indicates the state of the oscillating system at a given time, taking into account both the position and the direction of motion. Alright, I'll come again. Now, the best way to understand this is by using the circumference. So you understand what, when you think about phase, what it means. So let's assume we have something of this nature. We can be here, we can be here, we can be here, we can be here. We can be at any point in this circle. What phase is describing is giving us an idea of where the motion is. It's okay, is it here? If it's here, it gives details. Okay, this is the specific point at which it is. This is the time at which it's at this position. Like, it's giving us more details, right? So it's making our oscillation look putting it in perspective. So phase refers to the specific point in the circle of the oscillation. It indicates the state of the oscillation state at a given time, taking into consideration both the position and direction of motion. Now, there are two ways in which phase can be represented. One is the phase angle, and second is the instantaneous phase, right? Which have the formula this. Okay. All right. So now, phase angle. What does phase angle mean? All right. So phase angle is denoted by this. Right? So it's a constant that represents the initial angle at t equal to 0. It effectively determines the starting point of the oscillation within its circle. So one thing about the phase angle is that it determines the starting point of the oscillation. It tells you more, it gives you information about the starting point of the oscillation in this circle. Now, what you have to know that phase angle is actually what? T equal to 0. Clear? And determine the starting point of the oscillation. Now, for instantaneous phase, now whenever you hear instantaneous in physics, like wherever I hear it, it's all about real-time notification. Input that real-time notification. Oh, if it's happening at t equals to 2, right, it's telling you that, oh, it's really t equals to 2. If it's happening at t equals to 6, it's telling you that, oh, really t equals to 6. It's just like real-time information, real-time notification, real-time experience. Clear? Now, the instantaneous phase is the expression. Has the expression this, right? It describes the state of the oscillation at a specific point in time. Now, this is the formula at which they're representing. Now, this, as you know by now, is angular frequency, and t is the time. Now, simple harmonic motion. There are certain equations that you have to know. In short, these equations are very important as they are associated with simple harmonic motion, and as it might look vague now. Don't worry, just watch the video on the calculation aspect of this video. I get it. So this is just like an introductory class, and I just want you to get the concept, so that when we are solving questions, you'll be like, oh, where did this come from? Okay, now the displacement, which can be represented either by x or y, right? Now I'm making of x, right, is equal to a mean amplitude cos theta, or a cos theta. Like, this theta can be expanded, right, to include the instantaneous phase. Exactly. So a cos theta or a cos instantaneous phase, right? Good. So for displacement, when displacement is a cos theta or a cos stability plus phase angle, literally by differentiating this, right? So remember differentiation. This is not in mathematics video, so I don't want to just complicate things by differentiating it. But if we should differentiate this, right, we should differentiate it like the y or the x, the t, right? We're going to get our velocity, the v, right? We're going to get our velocity. So by differentiating, we have minus aw sine theta, or minus a angular frequency sine instantaneous phase. By differentiating this further, we have the a, meaning acceleration. Acceleration is equal to minus amplitude w square cos theta and on and on. So what if the displacement is a sine theta and not a cos theta? What happens? By differentiating it also, just follow the same step, we arrive at this. So what's the trend? What can you notice? First, we're starting with cos, we're ending with cos normal. So we're starting with cos, then sine, then cos. Do you get? Well, we're starting with cos, then sine, and cos, like that. We're starting with sine, then cos, and sine. But what you start with, you're going to end with. It's just a way of you cramming it. If you're not a mathematics student, but if you're a mathematics student, then learning the details of it won't be a problem, since you know about calculus and the rest like that, right? Alright, so the parameters which I've listed in the previous slide, this is the angular frequency, the t is the time, this is the phase angle which I've said, a is what? Amplitude, right? So this which I termed instantaneous phase is the phase of the oscillation. In this case, it accounts for both the progression of the wave over time and an initial displacement or shift. Okay, good. We're moving into the substance of this topic. I get it. So it's not all cases, it's not all time you are going to be given an angle. Sometimes you might not be given an angle, and then you might be told to actually find the velocity, right? You might be asked to find the velocity. What do you do now? By solving that formula, that is from v equal to, depending on where we are coming from, by v equals to minus a w cos theta. By solving from here, we can actually arrive at this. So v is equal to plus or minus w a square minus x square, right? There are several ways in which we can get this, so don't be confused. But just learn this. Velocity is equal to plus or minus angular frequency square root of amplitude square minus displacement square. What about acceleration? Acceleration is equal to minus w square x minus w square x. Now you have to notice something. When I started this video, I said it's directly proportional to what? X, but not just x. It's directly proportional to minus x. Why is it minus x? Remember that f is directly proportional to what? Minus x, which I explained couple of slides back, right? And we know that f, according to Newton's law of motion, is equal to ma. Clear? So we now have that a is directly proportional to f, too. You can say so. So by just replacing this, I can just say a is directly proportional to minus x. Is that clear? So key takeaway is that v is know this and what, then know this. Alright, so maximum velocity. What does maximum velocity mean? So maximum velocity is actually ascertained, or is actually reached, when the displacement is equal to 0. So in a simple pendulum now, right, that is a scenario, right? A scenario something like this. So at this point, the velocity is literally, let's say, 0. The velocity is 0 at this point, right? The energy is actually 0, right? The energy is 0. Why at this point the kinetic energy is greatest, and therefore the velocity is greatest at this position. Now this position is relative, in that I told you that amplitude and displacement is associated with distance. Exactly. So now displacement velocity is maximum. Sorry, I missed it up here. Sorry. Velocity is maximum at the neutral position. It's actually potential energy that is greatest at this position. Sorry for that. So kinetic energy is greatest at this position. Are you getting? Greatest is greatest at this position, while potential energy is greatest at this position. Now kinetic energy is equal to 1 over 2 mv square, right? So V is related to what? Kinetic energy, right? Good. So at the equilibrium position, velocity is greater than 0. Please take note. Please take note. At the equilibrium position, velocity is the greatest. Right? So what's the displacement at the equilibrium position? 0. The displacement is 0 at the equilibrium position. So now let's bring out this formula. V is equal to plus or minus W square root A square minus X square, right? So our plus or minus W, since we say that this is 0, we have just this, right? So we are left with W A only as square we cancel square root. So that's how I arrived at this formula. So sometimes you might just be asked to find the maximum velocity, so don't stress your life. This is what you're going to make use of. Alright, so maximum acceleration too. What is maximum acceleration? At what point is acceleration maximum? Okay, so the higher you go, the more it is to, the more impact you are going to feel when you fall. So if this is the ground level and I'm at this point and another person is at this point, who do you think will be more hot? Definitely the person at this point. I get it. So in simple harmonic motion, it's kind of the same principle kind of apply, right? So at this point, the restoring force is actually like very great. The restoring force is actually very great here. The restoring force, right? And I told you restoring force is associated with what? Acceleration, since by first Newton law of motion. Is that very clear? So maximum velocity, maximum acceleration is actually ascertained when the displacement, I get it, is equal to amplitude. When the displacement equals the what? Amplitude. Is that very clear? That's how we came about this particular formula. Now, just for recap, we know that velocity is equal to plus or minus angular velocity and angular frequency, amplitude square minus x square. Is that clear? V max is equal to W A, because this has to be what? 0. What of acceleration? You know that already. Normal acceleration is minus W square x. So at maximum acceleration, we know that x is equal to what? Amplitude. So we're now left with minus W square A. Is that clear? Alright, so we're going to be talking about the relationship now. We're going to talk about the relationship between quantities in simple harmonic motion. Alright, so the first is displacement. We're trying to relate displacement, acceleration, and force, as they tend to be very they tend to have something in common. Most specifically, force and acceleration very similar, right? It takes what you relate. So during the course of this, I'm going to be describing the phase relationship when acceleration, situation when acceleration is maximum, amplitude and energy, and also the summary, just giving you the key points you have to take away, the key takeaway point. Also, the second part is displacement and velocity or energy, and reason why they are antiphase. That is, they are not in sync. You get. So we're going to discuss their relationship together. Scenario when acceleration is maximum or zero. Also amplitude and time in relationship in relation to what we are discussing, and also key takeaway, key points you have to take home. Is that clear? Alright, so the first is phase relationship between displacement, acceleration, and force. Alright, so the first, displacement, as you've known now, that displacement is the distance from the equilibrium point, equilibrium position at any given time. Acceleration, which is the rate of change of velocity in simple harmonic motion, is proportional to displacement, but in opposite direction. It's proportional to displacement, but in opposite direction. Or force, according to Hooke's law, the restoring force is proportional to displacement, but act in opposite direction. So both acceleration and force act in opposite direction to displacement. So it's more or less like as force increases, displacement reduces. What of this? What can we bring out when acceleration is maximum? What can we bring up exactly? Right, the acceleration is maximum when the displacement is at its maximum. I said that. This is the second time I'm saying it. The acceleration is maximum when the displacement is at its maximum, either positive or negative amplitude. This is because the restoring force is greatest when the object is furthest from the equilibrium. I explained this when I said that the higher you go, the more impact you feel when you fall down. Alright, so amplitude and energy. Amplitude is the maximum displacement from the equilibrium position, while energy in simple harmonic motion is the total mechanical energy. The total mechanical energy in simple harmonic motion is constant and depends on amplitude. Right? It depends on amplitude. So the value you are going to get depends on amplitude. Now it might look a little bit vague now, but when we are solving questions, you will connect all the dots, you connect all and relate to all what I've been saying. Is that very clear? Alright, so things you have to just take note of based on all what I've said in this. At maximum displacement, that is at the point further away from the equilibrium position, it can be here in respect to this, right? So at this point, I guess potential energy is at its maximum. Now you should know that potential energy literally depends based from our simple machine and rest like that, and energy, right? It goes to mg, right? Now potential energy kind of depends on height, more like. So and at this point it has height. It's some distance away from the surface level. So at maximum displacement, potential energy is maximum, but kinetic energy is zero. Kinetic energy is only greatest at this particular point. Is that very clear? Now acceleration is maximum at the displacement too. Force is also maximum. Now to the second scenario, displacement and velocity are in antiphase. Now velocity, which refers to the change of displacement, in simple harmonic motion, velocity is out of phase with displacement by 90 degrees. Please, this is an exam question, don't forget. A typical MCQ. Now velocity is out of phase with displacement by how many degrees? 90 degrees. In some cases, they might not just tell you 90 degrees in a course to confuse you or to test your understanding. You should know that pi is synonymous to 180 degrees. So if I omitted 90 degrees, right? I can just say pi over 2 and I'll still be correct. Exactly. Good. So energy, either kinetic or potential energy, oscillate between energy, that's the total energy of a simple harmonic motion, can be divided into two phases, kinetic energy and potential energy. So in a simple harmonic motion, it actually oscillates. The total energy, the total mechanical energy oscillates between kinetic and potential forms. Velocity is maximum when displacement is what? 0. Don't forget this. Velocity is maximum when the displacement is what? 0. MCQ. Displacement is 0 when velocity is maximum. Displacement is 0 when velocity is maximum. So this is interchangeably. We're just changing what mean the terms. Alright, so what happens, or what can we say when the displacement is actually minimum? And when the displacement minimum at the equilibrium position, or close to the equilibrium position, right? So velocity is the maximum at the equilibrium position, right? Velocity kinetic energy is also maximum when displacement is 0, because all the energy is kinetic at this point. Potential energy is 0 when displacement is 0. I told you that potential energy is related to the height. I hope you have not forgotten that. Alright, so what can we ascertain in this in respect to amplitude and time? Amplitude is the maximum displacement. Now, amplitude is related to time, as the more the amplitude literally reduces with time. Amplitude literally reduces with time. So the time here is specified a point in the oscillation circle. Now what are we going to take? I've been seeing a lot of things now. So what's the key point? What do you need to understand out of this particular relationship? Now the system spends equal time moving from equilibrium to maximum displacement and back to it. This is a perfect system. In reality, it's not so, but in an ideal system, the system, right, or the system spends equal time moving from equilibrium to maximum displacement. At displacement equal to 0, that is at the equilibrium position, the system is moving the fastest. I told you that at x equals to 0, kinetic energy is at the greatest, is at the maximum. At maximum displacement, that is farther away from the equilibrium position, the system is momentarily stopped. The system is momentarily at rest, reversing the direction. Is that clear? So just like I've said in previous slide, amplitude varies with time. Amplitude is directly proportional to what? 1 over time. It decreases as time progresses. All vibratory are subject to energy loss due to friction, right? So viscosity of fluid friction, this is the same as saying oscillation at down to time. So what I'm trying to say in this statement is that a system, an oscillating system, will not continue in that state forever, except an energy is constantly being thrown up into the system, right? So in reality, an oscillating system is susceptible, right, or vulnerable to be damped. Damped simply means that this particular system, this particular oscillation reduces with time. And why does it reduce with time? It's not as if it's being chased by an evil spirit. It's just that some natural forces, most specifically viscosity, friction, reduces its amplitude with respect to time. Is that very clear? Alright, so in case you have any question based on all what I've been saying, do not hesitate to ask question. Alright, so energy in simple harmonic motion. Right now, this is very simple and it's very easy for you to comprehend since I've been saying it all this while. The energy changes between potential energy and kinetic energy from one point to another. Right, so in the course of a motion, it changes or alternate between kinetic, potential, kinetic, potential, kinetic, potential, and rest like that, right? So the combination of both gives what is known as total mechanical energy. Total mechanical energy. Exactly. So first, I'll start from one of the components, which is potential energy. Now, I know that you are used to potential energy is mgh. Yes, you are correct if you say mgh. But now, in simple harmonic motion, the gravity does not contribute much. Gravity does not contribute much to its outcome. So therefore, this formula is invalid. We have to go back to elasticity. Now, in elasticity, we devise that we say that energy is equal to what? Half Fe, right? I tend to like this formula. Energy is equal to what? Half Fe. Is that getting? So E here means extension, and we can also say E here means displacement. Exactly. Now, F according to Hooke's law, right, is equal to Ke, literally. Now it means that energy will also be equal to half what? K, right? E square. Is that very clear? Alright. So E here, I told you that it can be associated with displacement. So I can just say E is equal to half K X square. And that's how it came about this particular formula. So the potential energy is equal to half kx square, where k is the first constant, x is the what? Displacement. Yeah. So the first constant or spring constant is the same stuff. Is that very clear? And there is actually a formula that link angular frequency and spring constant together. Yeah, that is more like something that link them together. Exactly. And is this W square is equal to K over M. Is that very clear? K is equal to W square M. So if I should put this here, I can have EP, which is potential energy, is equal to half K, which is W square M X. So to make a formula more presentable, I can just say half mw square x. X what? Sorry, x square, exactly. X square, exactly. That's how I came about this formula. So either these or these are both correct, depending on how the question was asked. Now the second one is the kinetic energy. Now what do you understand by kinetic energy? This is simple. It doesn't change from what we know from normal energy, right? So the kinetic energy at any point in time in a simple harmonic motion is equal to half mv squared. Now the reason why this formula is still valid is that we talk about velocity here. We are also talking about mass of the object, mass of the small bulb. I get it. So we're not going to just proceed that way. We have to relate all what we know from the past to the present. Now, from the past, we know that kinetic energy is equal to half mv squared. But then, most questions might not appear this way. So how do we conquer it when they don't come in the fashion we are used to? Alright, so this is when this come up. Do you remember this? Exactly. When we were talking about equation, I brought this up. That velocity is equal to W, which is the angular frequency, square root A square amplitude square minus displacement square. Is that very clear? Alright, so if I should bring out this formula, which is half mv square, all I have to do is implement this. So it becomes half m, v is what? W square. Now remember that this is like this, so anything that I'm putting will affect it. So this will come here, but this specifically will cancel this. Show you get that way. So this is W square because of the square outside. The square is gone now, so we have a square x minus what? X square. Is that very clear? Good. So this is the formula you have to take note of in kinetic energy. Alright, so let me just this is like a revision for you now, because you understand the previous one, which is the most important. Now, for total mechanical energy, a system remains constant and is the sum of its kinetic energy and the potential energy. The total energy is the sum of the kinetic and the potential energy. Right? Energy at any point in the system, at any point, both at equilibrium, at amplitude, at the magnitude, any point at all, is equal to what? Potential energy plus kinetic energy. I get it. So we know the formula now. We know this formula. But if I should follow this route, you might not really get it. So we're going to go back to the the how I derive it. I get it. Now, starting from this point, if we were to add this together, right? Just like picking out what is most common and like that, you get that. We arrive at this. Remember, I said that K is equal to what? Can I try? W by M. Am I right? Alright, look at this formula again. I needed to get it. W square is equal to K over M. Just teasing you. So W square is equal to K over M. So this should be written as W square is equal to K over M. Right? So now K is equal to W square M. Clear? W square M. So that means I can change just this. I can change this and replace it with just K, and I'll still be correct. So that's why I said here straight up that total energy is what? Half Ka square, without any deliberation. Right? So the energy of a simple harmonic motion varies as the square of amplitude. It varies as the square of amplitude, right? So what that statement is trying to say that E, as we know now, is equal to half Ka square. Clear? It's equal to half Ka square, right? So E is directly proportional to A square. I guess amplitude is inversely proportional to T. Is still valid. I guess it's still valid. And energy is directly proportional to what? Half 1/2 is inversely proportional to what? Time square. Is that clear? Alright, so these are things, these are conditions that are associated with simple harmonic motion that I feel is important for you to know. The first is forced vibration, the second is resonance. Both of them are interlinked. So once you're able to understand one, you'll be able to get it. So I will not go straight. I will start by explaining what it really means. Okay, how many of you have actually used a pen to drum on the table, or used a drumming stick to drum on the drum? You'll notice that what determines the vibrational level is actually how hard you hit. So if you tap more, it might not vibrate much, but if you keep on hitting consecutively, you notice that you get the required sound, you get the sound which you really want. Now in that kind of case, we call it forced vibration. Yes, this system can vibrate, but then we're applying an external force, we're applying external energy. Is that clear? We're applying external energy to see that this system vibrates. So vibration of a body with the frequency of the vibrating agent, in this case the drumming stick, right? That rather than its own natural vibration when the body is continuously disturbed in a regular manner. So in forced vibration, this body, anybody at all, vibrates, right, based on the external force, in relative to the external force. The amplitude and the energy depend. So the how loud that this surface will vibrate depends on the difference between the frequencies, that is the natural frequency of the object and the frequency of the force. Of the force. So the greater the difference, the smaller the amplitude. But if they are very, very close together, you will hear a louder pitch, you will hear a louder sound. Exactly. Now in resonance, they are conditioned to there are certain conditions that this system, this body, has to position itself for a first vibration to become what? A resonance. I always put it that resonance is just a special case of what? Resonance. Resonance is actually a special case of first vibration. So in resonance, the forcing frequency becomes close or nearly equal to the natural frequency. Natural frequency in this case is talking about the body we are hitting. Good. And also in resonance, amplitude and energy increase to what? To the maximum, right? Because is actually coercing or getting everything it needs. Whoosh. Now, application of force, vibration, and resonance. First is children swing in playground. Now, you notice that for you to make that swing to move, you have to apply force. And that's how you apply this force, like it moves, oh my god. The way it moves freely. And if you want to make it to be in sync, you have to be applying that force, the same energy, at a specific interval of time. Right, at a specific interval. I get it. So that's an example of a forced vibration and also resonance in some case. Now, if you've ever walked across a gutter which had a plank, a long plank, you notice that the way that plank vibrates depends on your walking step. Right, at some point I used to be scared. I'd be like, oh my god, let's not break. So I'll keep on walking small, little by little, to ensure that I don't increase the amplitude of that plank. If not, it will break, right? And the reason why it will break is that it will have to accommodate your natural frequency. It has to accommodate this forced frequency. I get it. That's why you will notice that whenever soldiers are trying to cross a bridge, they actually break up. They don't go as a pack. Like I say, either they stop marching or they don't march in sync. Exactly. So they literally just break up. Also, simple pendulum with equal length vibrates. So what this means is that you can have a simple pendulum like this. They all have the same line. They all have the same length. I get it. So we can have another one like this. So this is not in sync, this is in sync. So simple pendulum with equal length vibrates in larger amplitude. So if I just increase this thing, like if I draw it here and release it, they will all vibrate at the same point. But if I draw this and release it, not all of them will respond to the motion. Is that very clear? Now, what are the examples of simple harmonic motion you have to know? The first is mass spring system. A mass is attached to a spring that oscillates back and forth when displaced from its equilibrium position. I explained this when I said that something like this, we can have something like this. I guess we can have something like this. Pendulum, I know you understand this by now, right? These both of them are common examples of simple harmonic motion. The last is the oscillating electric circuit. Now this is not very great to visualize. Since we're talking about current now, we're talking about circuits now. LC circuit, which is inductor capacitor circuit, can exhibit electric simple harmonic motion, where the charge and current oscillate sinusoidally. Alright, so what can you take out of this? What can you take out of this? What can you take out of this video? What do you learn? You should know that force is directly proportional to displacement. Acceleration is also directly proportional to what? To displacement too. And also we know that acceleration is equal to minus w square x, but at maximum it's equal to minus w square a being amplitude. Also we have v equal to plus or minus w square root a square minus x square. So at v maximum we have plus or minus, not even plus or minus now, we just have w a square. I guess it, because at maximum this will be what, 0. So oh sorry, this constant is so nothing be here. So it's actually v max because of w e. I don't cram formula, I just like flow along with what I'm doing. I get it. So you should learn that principle too. It's very important. So you already know the types of simple harmonic motion we have, what phase angle really mean, the denotation of phase angle, displacement, you know that now, amplitude, frequency, all these are important for you to actually take note of. Alright, thank you so much for taking our time. Thank you so much for staying with us till the end of this video. I'm very grateful, very grateful. Thank you, and don't go yet, don't go, wait. Oh yeah, subscribe. Try subscribing for more videos like this. Like, comment, share if it's possible, right, so that your friend can also benefit from a very wonderful video as this, right? So you can also follow us on our social media handles. We are at Official Gallant Tutors on Facebook, Telegram, X, formerly called Twitter, Instagram, etc. Right, so just follow us on all social media handles. Thank you for watching. Have a great day ahead. Bye.